Welcome back, and here we have another example of an application of derivatives problem involving velocity and acceleration. So here we have an equation s of t equals negative 4.9 t squared plus 520 t plus 100. And this gives the distance in meters from the ground of an object thrown vertically up in the air as a function of time in seconds. So part A, we're asked to find the initial velocity of the object. So first we will find velocity as a function of time, and then initial meaning at t equals 0, so we're going to plug in t equals 0 into that. So let's begin by finding v of t, taking the derivative of the given function. So bring the 2 down. It's going to be negative 9.8 t plus 520. Of course, derivative of a constant is 0, that disappears. Now initial velocity, plug in 0 for t, and we get 520. And the units will be, once again, meters per second. And I want you to notice something. When you're giving an equation, a quadratic equation, usually what happens is basically the coefficient of the t term turns out to be the initial velocity. And those of you taking physics, there's actually a general formula for projectile motion for the vertical component. It goes something like this: negative 1 over 2 gt squared plus v sub 0 t plus s sub 0. Like this represents the initial height, this represents initial velocity. The first coefficient is half of the gravitational constant. So you don't have to know any of that for this class, but you'll probably see that in physics. Okay, part B. What is the velocity 10 seconds later? So all we have to find is v of 10. So go back to the velocity equation and plug in 10 for time. Negative 9.8 times 10 plus 520. And that should give us 422 meters per second. So 10 seconds later, the object is still moving upwards, as indicated with a positive velocity, at a rate of 422 meters per second. Notice that it has slowed down, right? Due to the gravitational pull, in the beginning it has the highest velocities, and then as time goes by, it's getting less and less, basically its velocity is getting less and less, right? Okay. When does it reach the maximum height? By the way, technically you should be able to do every one of the parts of this question based on the first example. So I want to encourage you to get ahead here and then come back to check your answers. So when does it reach maximum height? Well, we just learned if this is your s of t equation, at the maximum height point, the derivative, the slope of the tangent line of s of t is 0. In other words, momentarily the velocity is 0. So if you set s prime equal to 0, also known as velocity equal to 0, we're going to find when that occurs. So let's do that. So negative 9.8 t plus 520 equals 0. I'm going to subtract 520 from both sides. Negative 9.8 t equals negative 520. So we get t equals negative 520 divided by negative 9.8. Notice they're both negative, so the result will be positive. And if you put that in the calculator, you should get roughly 53.06 seconds. And I have a rough graph over here, and you can see that it will make sense that the maximum height will be reached roughly at 53.06 seconds. Okay, what about the maximum height? So here we found the time down here, and so 53 seconds roughly after it was thrown up in the air is when the maximum height is obtained. But what is it in terms of meters? It looks like somewhere between 1,000 and 1,500, between 10,000 and 15,000 based on our graph there. So let's find the maximum height. So you just need to plug in the time that you obtain here into your distance from the ground equation. That was the original one. So let's do that. So S evaluated at 53.06 equals negative 4.9 times quantity 53.06 squared plus 520 times 53.06 plus 100. and we should easily be able to do this on the calculator. Sometimes I get a question like, sometimes students enter this and they said, okay, I'm getting an error message. Why is it not giving me the answer? Because when you start with a negative sign, like don't put the big minus sign that you see on the right side of your calculator. Like if you have a TI-83, don't use this minus sign. Instead, there's a little negation sign down below. There's like a little negation sign. Use that one when you're starting to enter your expression when it starts with a negative. Okay, so if I do all of that on the calculator, I'm getting roughly 13,895.9 meters. 13,895. And if I look at this graph, it was somewhere between 10,000 and 15,000. It all makes sense. And if I want to check this using Desmos, I'd like to show you something here. So I entered my equation up here as negative 9.9 t squared plus 520 t plus 100. And then that gives me something right away. Usually you're not going to like what you see because it's going to chop off the top of the graph. Then I go here using the graph settings icon, and I manually sometimes change my x and y values based on the results I obtain. Like if I obtain roughly 53.06 seconds, I want to make sure it's in the x-axis included. So I might go for the x, let's say, from negative 10 to, okay, 53 was the middle, so let me just go to, let's say, 125 to make sure I include all of that. So, you know, depending on what you select, the graph will look a little bit different. Let me go to 200. So I don't want to chop it off right here at the end. I want to have a little bit more before and after. So you can choose your settings accordingly for your X window and Y window. But this gives us a rough idea, and roughly speaking, the maximum height seems to be around here somewhere, and 53.06, and at a height of exactly what we got in the other page. Okay, so we can verify our answers that way. That's always helpful, using Desmos or also using your graphing calculator. Just go to y equals screen and enter your equation, and then with the window you can change your settings. I think there's also zoom fit that might give you the correct range, so you don't have to play with the settings manually. So going back to our example, let's continue. There's a few more parts to this question. Okay, one question is, when does the object reach the ground? Now notice this one did not start at 0 height, so it's not perfectly symmetrical, although because it's such a big height, it may look like it's perfectly symmetrical. But let's just do it the traditional way. So when does the object hit the ground? We need to set the distance from the ground equal to 0. So set s of t equal to 0. So that will be the original equation, which was negative 4.9 t squared plus 520 t plus 100. That was the original s of t, and we set that equal to 0. Now we notice that this is not going to be as easy to solve as the first problem we did in our first example in the other segment, because the other one didn't have the third term. This one has all three terms of your quadratic equation, and when the numbers are messy, I don't even bother trying to factor. I'm just going to go directly to the quadratic formula. Let me remind everybody, with the quadratic formula, you have negative of b plus or minus square root of b squared minus 4ac all over 2a. And of course, this is your a right here, this is your b, and this is your c. So let's plug everything into that formula, and we're going to have negative of b, so negative 520, plus or minus the square root of b squared minus 4ac. So 520 squared minus 4 times negative 4.9 times c, which is 100, everything under the square root sign, and then draw a long line below everything on the top, divide by 2a, so that's 2 times negative 4.9. Now you can enter this in your TI calculator, and I've noticed some of the newer calculators, if you press on their alpha y equals and then select option number 1 n/d, it will give you a nice fraction like this. So you can enter this much more easily on your calculator. So again, you need to do the alpha key in green, and right after it, the y equals key. And then select numerator over denominator, so it gives you a pretty fraction to work with, so you can enter everything nicely there. So if you are using Desmos, it also has a built-in calculator. It's not just a graphing feature, it's also a regular calculator. So I can show you how I enter this in Desmos. So it's right up here, so you can say negative 520. And by the way, when you're entering something in a new line, and there's down here, you see there is a little like a keyboard. If you click on that, it will give you the calculator. And then if you begin with this division sign, it gives you a nice fraction right away. So I click on the division sign, it gives me a fraction. So now on the top I can enter, like, and I'm using negative sign from the keyboard, negative 520 plus. For the square root, I can click on here, or if you just type the letters SQRT, it gives you a square root. And from here on, you just continue to type your expression. To save time, I'll just show you. I entered over here. So negative 520 plus the square root of everything we have on the other page. It's been entered here. Notice I'm using extra sets of parentheses, etc. to do this correctly. The only caution I have for you is if you have the older version of the calculator where you don't have a pretty, like a fraction bar, in that situation, when you're dividing by two things in the denominator, after your division sign, open a parenthesis and enter it as like 2 times negative 4.9. Otherwise, if you just do division by 2 times negative 4.9, it will divide by 2, but then it's going to multiply the whole thing by negative 4.9. So those are some things to be careful about when you're entering this on the calculator. So when we do this, there's a negative and there's a positive, so 2 possible answers. So notice when I put a plus in the middle, I got negative 0.19. And time cannot be negative, so I'm going to discard that solution. When I put a minus in the middle, that one gave me the solution 106.3. So that must be this point right here. So that's the only one I'll be able to accept as an answer for this question. So the solutions are negative 0.19 and 106.3. And this is the only one we're accepting, because even though this looks like 0 over here, if you zoom in, it was like a little bit above 0. So that one's really not a solution. It gives you the negative point. So, but the real solution is over here, and that is 106.3 seconds. That's when it hits the ground. 106.3 seconds after it was thrown up in the air. It comes back to hit the ground. Okay, the next question is, what is the velocity of the object as it hits the ground? Okay, so all we have to do is then find the velocity at this moment in time. That's the velocity at the moment of impact. It comes with that velocity, but a split second later, it will stop. But we need to find what that velocity is. So find v of 106.3. And so let me go back to the velocity equation, negative 9.8 t plus 520. Instead of t, go ahead and put in 106.3. And that one will give us negative 521.7 meter per second. Remember, it makes sense that it's negative at that moment in time because it's going downwards. If you draw the tangent line there, slope of the tangent line is negative. So it makes sense that velocity will be negative at that moment as it's hitting the ground. Also, before I move on to the other page, I want to show you something. Like when you do the quadratic formula, they're messy, and I'm entering like 1 with the plus, 1 with the minus. And all I did was like I copied the whole thing. So Control C, and then click on down below another line, and I did Control V. Then all I have to do was change this middle sign. If it was a plus, I change it to a minus. That makes it easier. On the graphing calculator, you have a similar option. You can use, once you get the answer for the first one, and it gives you, let's say, negative 0.19. Use the upper arrow key. It takes you to the previous line, which is this line. it will be highlighted, and then press enter. It will come and become your current line, and then you can just use the arrow key to go back and change it plus to a minus. The older versions of the calculator, the second enter, it reproduces a line from the top, and then with one simple thing you don't have to re-enter everything. Okay, so that's helpful when you're doing the quadratic formula. Okay, a few more questions about the same equation. When is the object 5,000 meters from the ground level? Okay, so if we think about that for a second. So when is it 5,000 meters above the ground level? Okay, so I got this gigantic graph, but I want to be able to show you here what's going on. So I'm going to draw a line roughly at the point of 5,000. Notice that will happen twice. Once like at this point here, called the t sub 1, and once at this point right here, called that t sub 2. So we expect there's going to be two answers to this question. When is it 5,000 meters from the ground level? So what we need to do is we need to set the distance equation equal to 5,000 and solve for t. That will give us the time when the object is exactly 5,000 meters from the ground level. Okay, to do that we need to remember our S of t equation and set that equal to 5,000. So 5,000 equals, you can look it up from the other page, but it was negative 4.9 t squared plus 520 t plus 100. And this is another quadratic equation, so I'm going to subtract 5,000, get 0 on one side to obtain negative 4.9 t squared plus 520 t. And if you have 100 minus 5,000, you're going to have negative 4,900 as your last term. Notice again, this is not easy to factor. There's no simple way to take out just a t or anything like that. We're going to have to use the quadratic formula once again. So this will be a great time for you to pause the video, and when you come back, I'm just going to show the answer to you so you can check your work. Okay, so hopefully you already tried it, and I just used the quadratic formula once again. And when we simplify this, it turns out that we're going to have two answers, and I've already entered them over here. So it's this one and this one. So when you have a negative 520 minus that big square root over the quantity 2 times negative 4.9, you're going to get 95.6 or 95.7 roughly. And when you have a plus in the middle, you're going to get 10.45 or 10.5 roughly. So those are going to be the answers for that question. So 2 moments in time at 10.5 seconds, also 95.7 seconds. And based on this graph, again, we can see that makes sense. There are 2 times when the height from the ground will be exactly 5,000 meters. And then I think I have one last part of this question. When is the velocity equal to 200 meters per second? So for that one, as you may have guessed it, basically we need to set the velocity equal to 200. So be careful when you're plugging a value in for t versus when you're setting everything equal to a value. The problem really pretty much tells you what to do. In this case, when is the velocity equal to 200, right? So set velocity equal to 200. And from there, solve for t. And we know the velocity equation was negative 9.8 t plus 520, negative 9.8 t plus 520. And we're not plugging in t equals 200. They didn't say time equals 200 seconds or anything like that. They said when is the velocity equal to 200. So set the entire velocity equal to 200. And we're going to solve for t to answer the question when. So first subtract 520 from both sides. Luckily, no more quadratic equations, right? This one's nice and linear. So on that side, I'm getting negative 320 equals negative 9.8 t on the left, and divide both sides with negative 9.8. And that will give us a positive answer of 32.7 seconds. So now we found the moment in time when velocity is 200, and looking at this graph, basically we're finding the moment when the slope of the tangent line is 200, and the answer is roughly 32. So this was like 53 roughly in the middle, so 32, very roughly speaking. At that moment in time, the slope of the tangent line, or the velocity, is 200. Okay, so that's pretty much summarized, and you're going to have all kinds of variations of this type of question, but I think this one was very comprehensive. And if you watched me do all the steps, you may want to cover it up again and maybe see if you can do it on your own before you tackle the homework questions. And there's one more example, but I'm going to go over that one in the next segment. And that's not velocity, a different type of application.